features is this. Once we do apply, we linearize the system, then basically that is the answer you're supposed to provide. Okay, and again, this one is a constant, this one is a constant. Basically, this system will be somehow in the form like the linearized systems. I would say this Linearized system somehow looks like a plus m times x minus x0. Okay, a is a constant given by this, m is a slope of this linear system given by this function derivative. You calculate that derivative at this one, and then this one tell you how much is away from this operation system. Okay, and we'll look at this graph. So from here, this graph you can see for this green curve represent is a certain nonlinear functions, and that's a function of, for example, in terms of parameter t. Okay, basically these are nonlinear functions, and now we determine we want to linearize the system at here. So basically from here we simply graphically to represent the linearized system is represented by the black line. This black line has the slope, and basic slope is equal to this term as I point out there. Okay, and as far as what is the x minus x0, then that one. So this is, for example, let me change my parameter. Let me change my parameters, say this is x, okay? So this point is x0. So now I want to explain graphically what is x minus x0. So for example, here this is the x, and the point x. So this x minus x0 representing is, for example, from the linearized system is this value here. However, the true values of the original system is here on the green curve. So you can see what is the difference. This value is calculated based upon the linearized system. It's deviated or have discrepancies between from the real values. So this one is given by the approximated terms. Those ones are the terms we ignored. We force them to ignore for a linear system. So you can see if you operate based upon the operations point and you want to predict the system response at a certain value, that value shouldn't be too far away from this point. Otherwise, the value you estimated will have a large discrepancies from it's supposed to be. So the point in one in conclusion is this: for linear systems, if you're going to operate, which means if you're going to extrapolate the value, you suppose you must confine the range of x is very small away from x0. If x is too large, then what will be the next step? The next step is this. Say right now, for example, for this linear system to be good, then say this is the valid. This is I would say this is a valid operation range for x. If you have another x, hey, I want to know the value of x here. Then what you can do? You simply pick up this one. You say this is x1. Okay, now I simply linearize the system at the new value x1. Okay, so you keep changing the point of operation for linearizations, and then you can always have a good approximation. Say, right now, if you want to estimate the system behavior at here x, then you simply move the linearize the operation point to nearby where you want to just go forward to work on the new system. For the linearized system about this point, then you can expect that we'll have a different value of the a, and we'll have a different value of n. Are we good? Okay, good. So that is the point of the linearizations. And in the second homework, I think I designed only one or two simple kind of the exercise for that kind of calculations. Okay, just give it a try. So by doing so, I think I finished the slides of these sections. Okay, so that is the one, and here we have a simple exercise. Probably you can refer by yourself. You can exercise by yourself. Okay, so simply this is a very easy one. You can refer to the slides there. Okay, mathematically is we simply apply Taylor series expansion. I think this kind of topic should be in algebra, the pre-cal, right? The high school. Okay, so that is the these topics. Before we move to the second, and here I think I'm going to talk about is the modeling, and this will be very quick. So any questions so far, or any questions about doing your homework? No? Okay, I'm going to post the solution probably tonight. Okay, because later on, once after class, I'm going to have the some training, and then I won't be able to do it. Okay, probably tonight. So now we go to the new topic, and this one basically will cover our textbook, chapter 2, chapter 3, and even chapter 4. And the modeling of the physical systems won't be the focus of the control. No. And suppose if you have taken other classes like the thermal systems, the heat and mass transfer, and then machine design or machinery, the dynamics of machinery, so those kind of things will help you more or less for building up a good modeling. Okay, so here for this is I'm going to take maybe at most 1 lecture hours and just quickly go over something, and will be very fundamental, very basic modeling techniques, and that one from your point of view, that should be very super easy. So here I want to review a force system mechanical, and basically that is the more on the vibration kind of modeling. Electrical system pretty much covered by your 307, and fluid flow system, that one I won't go to Newton, the Navier-Stokes equation, no. Okay, so basically that one will be only for the hydraulic static the problems, and thermal system will be I will try to ignore that part. Okay. Mechanical systems, I think this will take in the majority of our exercise in your homework too. And here, basically, we're going to apply Newton's second law to simplify, to model the spring, mass, damper, vibration systems. And if you have taken vibrations, then that's good for you. And here will be good refresh of the memories you did last semester or in every fall. Otherwise, if you have not taken vibration system, I think you can take this advantage to learn the basic modeling techniques, and then hopefully will help you in the coming fall. Okay, so for vibration systems, the first one we will deal with is the combination of the multiple springs. And for example, with spring can be combined in parallel combination or in series combinations. Then in either way, our interest is to find equivalent spring constant. So for example here, for taking this opportunity, taking this example here, so if we have the parallel spring system, let me call this is K1, K2. So what is the equivalent descriptions of the KEQ? Okay, so for example here is the force we applied. So this is the equivalent descriptions. So we want to find out the equivalent value of the KEQ that will have the same performance, will give you the same performance like this one. And my notation of this one basically is the spring clamped to the wall. Okay, so that's the notation of the drawing. In terms of equation, basically for this one, equation is KEQ simply is the summation of the two springs. And the reason why you can take free body diagrams quickly, and free body diagram you can take is taking about, you can take about this, and this one usually is indicate, this means this is a rigid plate. Rigid, that means no deformations, and it will bear no deformation. Rigid plate basically is physical role is to simply to transmit force. Okay, so that's the meaning of that one. So for this rigid plate, you can take free body diagram on this one. So let me draw the free body diagram here. Okay, so free body diagram of this one, this is a given force here. So assuming this rigid body plate being displaced due to this force by certain distance, so say, let me say using this notation here, I said this one be displaced to here by x, okay? Due to this displacement, then the spring will produce the counterbalance force try to recover, so this is K1x, and this is K2x, okay? So that is in the free body diagram, and this system will be in static, in equilibrium. So for this modeling, we assume everything is in static equilibrium. So that means by force equilibrium in both directions, then that will be K1x plus K2x. Okay. So that is a result of the force equilibrium. And then from mathematics, then here you can see we can keep writing the two terms. We term the x here, and that basically is K1 plus K2. Okay, so that means F equal to this. So once we have this one, you can see F equal to this is the spring constant multiplied with x. So basically this is our displacement x. So that means here we figure out the KEQ is supposed to be equal to this one. Okay, so this one is simply done by equilibrium. And again, for this one, if in series combinations, again, you can take the free body diagram on this piece. How to say? You can take free body diagram at this point and at this point. Okay, basically in here, say suppose the spring relative to the wall here, it has displaced by y, and this point respect to this point has respect to wall has displaced the distance by x. So here we can try to formulate is this. So if you like, you can try is this. So this is the spring here. Let me do that one again. K1, and the displacement. This is the x, and then here we have another K2, and this one displacement respect to the reference is y here. So here is our given force here. Okay. So again, the force, because this is in series combinations, by taking the free body diagram of this spring, K2. Okay, so K2, assuming K2 has the relative displacement y minus x, assuming y, for example, if y is longer than x, then K2 has been stretched. Okay, so that means K2 times y minus x, that is a force being stretched by the spring, and that one will be equal to F. So from here, F equal to K2 times y minus x. So that is from the spring, from the free body diagram of these portions. On the other side, because they are in series combinations, so the force being transmitted to here. So basically here we're taking the free body diagram of the K1 here. So K1, due to the displacement x, it will produce the counter force, the recurrent force K1x, and that one, again, this is transmitted at this point due to action-reaction, that is a force F. So basically, this is F here, so that means K1x equal to F. Okay? So from here, we combine the since I kind of in my writing it, I use an xy here is xy kind of swap. Basically, combining the two equations, we have this one. Okay. So from the two equations, we perceive the value here, then basically should be easily to find out the KEQ equal to the this value here. Okay, so in this combination, the KEQ inverse equal to this one. So basically, the two are pretty much generic. So that means doesn't matter how many numbers of the spring you have. For example, here if you have 3 springs, then basically here will be another additional term will be 1 over K3, then plus together equal to this one, etc. Okay, and if you have more complicated systems, I think this page, this kind of the Fermat diagram calculation can be the good base for you. The same thing, this is called the dampers, and damper provides the damping, which means a resistance to the movement. So the same thing here is the damping coefficient, and damping coefficient B1, B2 here we're using the symbol B, and damping coefficients can be related to the damping ratio zeta. You remember last time we talked about the second order differential system zeta, and zeta we call the damping ratio. Okay, damping ratio is a non-dimensional numbers, which means has no unit. Damping coefficient basically has unit. Basically, it is a function of the force and also is a function of the speed in the two relative points. This damper, basically you can imagine is just like the car's suspension system. Suspension system, if you park your car there, basically once car has no relative bumping, then basically if there's no relative bumping, basically suspension won't react, right? As long as you have a relative the bumping, then basically between the 2 points of the dampers, there's a relative velocity. The larger the velocity, the larger the damping force going to provide. So basically the damper is based upon the relative speed between its 2 points, 2 ends. Okay. So again, whatever the damping we have, then in parallel combinations, the same thing, have the same pattern as a spring here. Okay. So that is for the damper. This one is the real spring mass system, and here I can take we can take the exercise how to model this. So for this system, and here we can re-describe the system like this. So here we have a mass, and we simply draw a block to represent mass. Okay, and that has a mass. The m equal to mass of the system, and that system is supported by a spring. So assuming the spring is linear spring, we call the constant k, and also due to the movement, so the wall between the mass and the wall, they have a friction. Okay, so friction, assuming we have kind of lubricated, so assuming that can be described by certain kind of damper system, and then we call the using symbol here is using B. Okay. So spring constant, this is spring coefficient and damping coefficient and the mass. So that is the system. So when the system is going to take subject to a loading, so here it's called the F of t. So F of t can be an arbitrary external loading, and F of t can be a stationary. Sorry, this is the time. Okay, so basically this is the dynamic loading. So here from the equilibrium positions of the mass, we define the degree of freedom. So this is x of t. X of t is the displacement. We sometimes call the degree of freedom. Displacement measured from the static equilibrium positions of the mass block. And here I want to explain to you what is a static equilibrium positions. Static equilibrium position is this. So here we have, this is the mass, okay, and say I hold it, and right now I hold it, okay, and then this one being hang on by the spring, okay, here, okay, so I hang on here, I'm still hold it, and then I gradually release my hand. So this will, due to its own weight, this one will displace a little bit to be in balance with the spring. So now at this moment I remove my hand away, and then in this way this mass block is in equilibrium with the spring, just hang on there. So this is called the static equilibrium positions. In the static equilibrium positions, the spring has been deformed a little bit to counterbalance the weight of the block. Okay, and we measure the degree of freedom or displacement in our modeling from these particular positions. You good? Okay. Okay. Now from here. So from here, assuming we have, say, we displace the mass block by xt. So basically here, if the mass, say, you want to move down by x, and due to this is a loading we applied, so that is external loading first. And assuming this one had a degree of freedom exists, so due to mx double dot, the initial force, and that is the force there. I suppose I shouldn't be doing this way. Let me rephrase my words. This is the loading the mass block. Okay, so once this mass have displacement x, then external force is F, and here due to this movement, move down, for example, then the spring force will try to recover, so the spring force going up. And assuming, and here assuming also the displacement velocity, I would say the velocity is x dot going down as well, so the damper will provide a force bx dot opposite to the movement. Okay, opposite to the velocity. Okay, and now this one, this is a force, and due to Newton's second law, all the force must be to provide the initial force. So that means this one must be equal to mx double dot. Be good? So this equal sign is to apply Newton's second law. That means the mx double dot equal to all the forces, and that is the one we here apply here. Okay, so from here you can see basically we can write the equations here. So say mx will be equal to all the forces, assuming we take the sign convention positive downward. So mx equal to f of t and minus bx x dot minus kx. Okay, so here we converted mx dot plus bx dot plus kx equal to f of t. So this is the governing equations for this simple system. Be good? Okay, so the key is this: you define your degree of freedom first, and then you take the free body diagrams on the mass block to analyze all the given forces and the produced forces, and then you apply Newton's second law to formulate the equations. Okay, so from here we have that one basically mx double dot bx dot plus kx, and that is this equation here. And now for this example, we can try, and basically that is the similar way, and we see how can we do it. YU, okay. And here we have, let me do the little bit more general. So this is the given force F. Okay, F is a given external loading. So now from this case, let me define the degree of freedom. And the degree of freedom of the mass block is defined by y. So that means here we defined by y here. So again, we measure the degree of freedom from its static equilibrium positions. For this one to link it horizontally, assuming the gravity is down vertically. So basically for here, the equilibrium position basically corresponding to the spring has no deformation. Okay. And rather than, okay, now the difference between the previous example is rather than defining this is the wall, but here I would say this one is also moved. So basically this one has its own displacement that is characterized by u. Okay. So basically assuming this one can be, say, you have a spring damper system being linked onto your car is moving. Okay, and rather than you put that one onto the wall. Okay, so that's the difference. So here we have one more. I would say the freedom here is u. So for this system, in the similar way, we can try is this. We take the free body diagrams on the mass block. Okay, and here is the sinking tips, and you can assume once the two are in motion, you can assume y is greater than y. Okay, so here in the following, the modeling process, you assume u is greater than y, and then all the modeling must be consistent with this assumption. Okay, you may also assume y smaller than y, then you be consistent with everything on your assumption. Either way, the result will be the same. Okay, but in my personal opinion, my preference, I like to have the y larger than u. That is my kind of the mental operation. I like that way. Okay, so now under this case, again, we try to dig out what are the forces applied on this. The first one, this is a given, and nothing much to say. We just follow it. And now we assume y is greater than u, then basically you can say this portion, this point will, relative to this point, the distance will be stretched in this way, right? Because y is moving larger than u. So basically, eventually the mass block, respect to this one, the mass block will be somehow going to here, right? Based upon this assumption. Under this situation, then the spring will be trying to recover. So that means this is the direction of the recovering spring force. And how much? K times the deformation of a spring, which is y minus u. Right? Okay, the same thing. This is the recovering force from dampered, and that is, and I like to use C. Okay, so C times y dot minus u dot. If you assume y is less than u, then this direction of this arrow will opposite. You can double check. Okay, so that reason I'm saying stick with your assumption, then make everything consistent. So this one will be equal to basically will be equal to m y double dot. Okay, so that is Newton's law. Because the m going to have the initial force m times its own y double dot, the accelerations. So here we can write up m double dot will be equal to f of t. Assuming the sign convention positive rightwards. Okay, so minus c y dot minus u dot and minus k and y minus u. Okay, so under these situations, that is the equations like we have here. And for this example, we don't have external force, but here I added up 1 over ft. So that means if you like, you can move the things to, you can further arrange, but let me stop this exercise here. Are we good? Okay.